Thank you very much, ladies and gentlemen. Good afternoon. So this work is about numerical modeling of titanium scaffolds produced by this additive manufacturing method. So the outline is, first of all, I would like to show you what these materials are. And then we study their fatigue behavior, which was the motivation for the numerical modeling. So then I will show you the model and what it predicts, and I will summarize my talk. So maybe you saw them before, but scaffolds are porous structures, lattices like these, and here these are ceramics shown in bone repair, which is also interesting for us. And the reason why they are used here is because when the bone defect is larger than several micrometers, the bone cannot heal itself, and something like this is needed. And the additive manufacturing method is direct in writing. We are using is not so common as power bed fusion methods, so it needs some introduction. And this one is actually printing, because this one uses something called ink. And the ink is prepared by mixing powder. This can be the same powder as for power bed fusion processes, or it can be irregular powder, which is used for thermal spraying. So it is quite flexible. And this is mixed with polymeric binder, water, and you prepare the ink, which has special rheological properties. So you are able to create, based on the computer-aided design, the desired object. And the post-treatment includes, first of all, drying of water, then burning out the binder, and the last step of this technology is sintering. And as with other technologies which use sintering as the last step, this allows you to control the internal porosity of material. So here are examples of two types of materials we tested in fatigue. And as you can see, this one, which was sintered at 1400 for 10 hours, has very low porosity, and also it has larger grains because the temperature was higher. And this is porosity about 15%. And as you can see here, this is open porosity. We have one large pore across the whole filament we printed. And this is quite useful in biomedicine, because first of all, we reduce stiffness closer to the bone, which is needed. And also it provides additional space for cells to attach, and you can also use this internal pore for storage of healing substances, and when you can release them, so it's quite useful. We did fatigue experiments on these materials, and it was really very surprising, because we observed that the porous structures, which are here in red, are much better. So, for instance, here you can see we are somewhere beyond 10 to the power of 4 cycles to fail, and this is one order of magnitude higher fatigue, like in these materials. The samples we tested look like these cylinders, and we tested them under compression with R of 10. But as I told you, these materials differ not only in porosity. We have large pores here and small and less porosity here, but they also have different grain size. And as you can see here, they also have, because of different sintering regimes, they have different surface roughness. But clearly, they also differ in their fracture surfaces, where here you can see very rough fracture surface of filaments, while here in the compact samples, the fracture is quite smooth. So when we consider at all these differences between these two materials, the answer to the question why has been fatigue strength enhanced, at least what we think, is shown in this picture. The dominant aspect here is the interaction of crack with the pores. So we have really high roughness. We have a lot of secondary cracks, which are shown here by arrows. And if there were any positive effect of small grains in fatigue crack initiation, it seems to be negated by or counteracted by the surface roughness. And it seems to be observed in experiments. So here what is plotted is the change of the width of the hysteresis curve during experiments. And this is at the half lifetime, and this is a 3/4 lifetime. And if we focus just in this part, which I denoted quite arbitrarily here as high cycle fatigue, we see that in porous structure we have detectable damage, while the damage strain is much lower, and it's actually negative here for compact samples. So it seems that fatigue crack initiation is faster in porous materials, but the propagation of long cracks is really much slower than in compact samples. So the assumption is that the higher fatigue strength of porous materials is a consequence of microporosity-induced shielding effects, which retards the growth of long cracks. And here we can see what we saw in previous slide. This is taken from a book by Professor Jaroslav Pokluda. So this is in duplex steel, but we have branching, which decreases crack driving force, and also all the energy invested in these cracks, which do not continue, is lost, basically. We also have much rougher crack front, which means that at each segment of the crack front we have a mixed mode loading instead of pure mode 1 loading. So this also decreases crack driving force. And then we have much higher roughness of crack surfaces. So if we have shear misfit, we have high roughness induced crack closure. And here I should remind you that these are porous structures. So if any filament breaks, it tends to shear. So we have a shear in these structures. So these effects we think are really important here. And this is the unified model of crack tip shielding, which we try to use, or at least some of the part, because we haven't yet evaluated the fraction of branch crack, the contribution of crack branching. And what this model, this is the relative crack speed relative to the straight, perfectly straight crack front. So what this model tells us, and it's quite obvious, if we take the ratio of these relative speeds of compact and porous samples, we find that all these parameters, like the fraction of deflected crack front, roughness of the crack front, roughness surface of the crack flanks, is higher for porous structure, and the driving force relative is lower. So it predicts, and it is quite understandable that the crack growth rate is much higher in compact samples. We actually evaluated these two parts, and what we had was like 8 times higher speed in compact samples. But this model was developed for dense materials, so it doesn't include anti-shielding effects like lowering of Young modulus, interaction with pores. So we want to extend this model, and therefore we modeled these scaffolds, and we wanted to find what is the dependence of Young modulus on the microporosity to be included in the shielding model. And we were also interested on local plastic strain amplitude at critical sites to be able to think more about the length of the crack initiation in these materials. So the model is a 2-level model, and on the material scale, we use BCC arrangement of spherical pores, which is maybe better seen from here, where we have part of the spherical pore coming out of the corner of this cube, and the other is on the opposite corner. And we evaluated 4 different porosities, tensile properties, and then we modeled the scaffold, which is basically the same as the one we use in fatigue experiments. Okay. So this is just 4 material parameters we taken from this experimental paper, and with some additional experiments we were able, publishing the literature, we were also able to find for our specimen the fracture plastic strain. So here are the results of the tensile test of the material. And this was then transferred to the scaffold model. But let me point you, it is interesting to find out that the fracture strength is maximized for values like porosity of 20 or 25. So this means that we should do some experiments on materials with higher microporosity, perhaps. And here is the elastic modulus. And it's quite good to find out that this is in perfect agreement with this very old equation. So we can use this in our Unify model. And finally, here are the plastic strains, which are for loadings we use in our fatigue experiments. And therefore, we find out this paper published recently in the International Journal Fatigue, where they experimentally measured for pure titanium the length of the crack initiation versus the applied strain amplitude and plastic amplitude. And when we convert our numbers, we find out that the initiation in these materials is really short. So much longer fatigue life seems to be really possible to explain only by longer crack propagation. And here is the summary of what I said, but because there is probably not much time, I'm going to read it. Okay, thank you.